Okay, great. So I think we have everything set up. So I'll begin by welcoming everyone. So good morning, good evening, wherever you are. So today we're going to have the QISS seminar. It's going to be hosted on the topic of non-perturbative quantum gravity. As usual, the talk will be approximately 30 to 40 minutes, and there'll be plenty of time afterwards for questions and to discuss results. The talk is being live streamed and recorded. Please ask any clarifying questions if you have. But yes, any kind of longer questions, we have plenty of time at the end. So with that, I'll leave it to our speaker to introduce themselves and take it away. So thank you very much. I'll leave the floor to you.
Yes, thank you, Matt. Thanks for the invitation. Was I supposed to introduce myself?
Oh, sorry.
Beyond what's written on on my slide.
Yes.
Yes. Anyway, yes. So I'm Renate Loll, and I work on quantum gravity, and I am at the Radboud University in Nijmegen in the Netherlands. And yeah, we'll explain you about the beauties and new possibilities of going really non-perturbative in quantum gravity and what it is all about and what the benefits are. So here, my starting slide, should give you already kind of a flavor of what's to come. So here in the top left, that's kind of, the type of quantum space-times I'll be summing over in my path integral. And these look, of course, crazy and wild, but nevertheless, if one asks the right questions and measures the outcome, then one can map them sometimes to kind of classical expectations in the sense of expectation value. So here on the right, you see a particular observable that has been studied that has to do with curvature. So this is kind of this, already gives you an idea. And I was asked to explain my perspective on quantum gravity. So that's what this first slide is about in a nutshell. So it is about a functioning theoretical and computational framework, lattice quantum gravity, formulated in a particular way in terms of causal dynamical triangulations, or CDT for short. And it describes four-dimensional quantum gravity as a non-perturbative, diffeomorphism invariant quantum field theory of dynamical geometry. There are no exotic ingredients and no proliferation of free parameters. So it's basically just, in this case, a couple of free parameters. And you can perform numerical experiments. So we're making quantum gravity into an experimental science, if you like, but of course not really, but we have numerical experiments that allow us to look close to the Planck scale and really understand in the hitherto kind of unexplored regime within about 20 Planck lengths, 0 between 5 and 20 Planck lengths. And there are lots of surprises when we start studying observables, things you wouldn't have guessed just coming from, classical GR. This provides a blueprint, amongst other things, for the emergence of quantum spacetime. So one can show that the quantum spacetime emerges there from just a quantum superposition, which I described as a primordial soup, or you could think a quantum form of quantum excitations. And it gives us a new and more physical perspective on quantum gravity. So it's, in one sense, it highlights a non-perturbative nature, but as a consequence, the kind of phenomenology we can hope to be able to describe with it and derive from it. And there has been a lot of progress. So in this short synopsis, there are a few things which I want to highlight because they're important. So first of all, we have, a framework that's not just, a set of theoretical ideas, but it actually works in the sense that there is a computational tool that comes with it that allows us to derive quantitative statements to measure observables. So it's in 4D, that's important. Of course, there are lots of interesting things to be said about lower dimensional toy models, but this year is focused on 4D. Non-perturbative is really very essential. Diffeomorphism invariant, that is what makes gravity special compared to something like gauge theories. And it's not quantum mechanics, but it's a quantum field theory. And again, different from our theories, geometry is dynamical. So there's no fixed background anywhere. The numerical experiments I have already highlighted, and the observables do play a key role in extracting physical statements from this formulation. As I said, it gives us a blueprint. So many people talk about emergence, and it's beloved, and it's used, in so many different senses, and in a very, let's say, often not very literal sense. But here it's literally, I have a system of microscopic quantum degrees of freedom, and I look at them at sufficiently large, and coarse-grained scales, and then I can find, if I ask the right questions, if I look at the right observables, I can find some matches with properties I would expect from a classical space-time as given to me by general relativity. So this goes beyond what many approaches to quantum gravity can give you, because we've solved a whole lot of technical issues, and it's now already there. There's a tool, and one can start, or we have already started, of course, looking at genuine physical questions. So it's driven by asking interesting questions about physics that go beyond any specific approach. And of course, that's where, excitingly, eventually, we want to connect to phenomenology. And that will be, in the first place, kind of cosmology, early universe cosmology. And there's a lot of progress. And that's what part of the rest of my talk is about. So if you're interested in a larger context, also how to place that in the universe of quantum gravity formulations, I point you here to this relatively recent paper with this quantum gravity in 30 questions. So here are some key takeaways. So these are things that will come back maybe during the course of my talk, with some further explanation, but here they are up front. So my main message is going non-perturbative is really key to progress in quantum gravity. So one has to take the non-perturbative and background independent nature seriously. But of course, one needs the right tools. So our tools are within a framework which I would simply call lattice quantum gravity. In a specific formulation, kind of, I would say that the most powerful form of lattice gravity we know about. But not only that, it's, to my mind, the only known way to make sense of the gravitational path integral beyond 2D toy models, which are popular, but don't have very little to do with the real theory, beyond perturbation theory. Of course, we know quantum gravity is not perturbatively renormalizable, and also without making a truncation, via some symmetry arguments of the full set of degrees of freedom of gravity. So we are not doing quantum cosmology, but we're doing full quantum gravity. Now, one key finding that comes from this approach and has been known for a while is that really, if one looks non-perturbatively, then Euclidean and Lorentzian path integrals for gravity are inequivalent. Why do you want to look at Euclidean path integrals at all? Well, that has been done many times in order to simplify matters, a point I'll get back to. And what moreover happens, so in 4 dimensions, it seems that imposing a causal structure on individual path integral histories is kind of key and essential to get a good classical limit out. So that's also an important message, and also for everyone who loves causal structures and causality. Numerical tools are critical. They simply reach where other methods don't, although they are not very commonly used, and there is a lot of, maybe hesitation in part of the theoretical high energy community, including quantum gravity, to do anything then, and on paper manipulations, but that's changing. So what also is kind of an outcome of this analysis, this approach, is that, well, having a concrete window and being able to ask physical questions and actually to make measurements and finding things, one understands how different non-perturbative quantum gravity is from what we are used to and what our intuition is based on, which is classical GR, what we've learned from the textbook, or perturbative treatments. So therefore, there are actually what I would call many unrealistic expectations what a fundamental theory of quantum gravity will look like and what it be able to do and what kind of problems it will be able to solve. So we'll also get to this. So what I'm advocating in a way, and what comes out of looking at things non-perturbatively, is what I call quantum gravity without G mu nu. So what does that mean? Well, we're in a regime of the theory where tensor calculus not only is not readily available, but I would argue is just not the right tool to describe. So we are talking about a very non-perturbative regime, highly quantum fluctuating situation. There is no background, there are no coordinates, and well, G mu nu goes out of the window. So you'd say, okay, oh my gosh, I have a very powerful tool and this is now gone. You know, I don't know what I should do. But well, there is a lot of things to do, and in a way, it's very Einsteinian because one is thrown back at really thinking about what geometry is all about. So it has underappreciated benefits, but it has also technical benefits when it comes to formulating the path integral. So it's a bug. It's not a bug, but a feature of going non-perturbative. And what's in the background, and what I think is also very interesting, but I won't have very much time to say much about in my half hour, is that one has to go beyond, mathematically speaking, beyond smooth Riemannian or pseudo-Riemannian, that is Lorentzian geometry. So, and one of key tool is what I would call random geometry. Another is, you know, discrete ways of thinking about geometry, thinking about metric spaces that are not necessarily smooth. So that turns out is important. Okay, so let's get started on what this formalism is I'm using. So as I said, it's a way of doing the gravitational path integral. So here is a pure gravity path integral in the, you know, in this yellow box. So this is a very formal expression one writes down. Z is just the path integral. Here we're integrating, of course, functionally integrating over G. So what's G? G are geometries. So geometries live in a space of Lorentzian signature, metrics, modulo diffeomorphism. So that's the way we describe them when we come from the continuum theory. And each of them, so here's some to be specified measure, and then we are just, you know, integrating over all of these G's, and each one gets a weight that knows about complex weight, which depends on, you know, your favorite gravitational action in 4D. So this object is also sometimes called the sum over histories, because a history is just a space-time. So space as it evolves in time. And of course, you know, to make, well, boundary conditions should be specified, etc. So I'm skipping these details. So this is our statement of intent. This to define this quantity and, you know, to give meaning to its ingredients. So and particularly I'm going to study it in a non-perturbative context. So I'm not splitting this up into, you know, G's, G mu nu equal to eta mu nu, so Minkowski metric plus little fluctuations, but I allow arbitrarily curved metrics here in the sum. Now, this is of course totally ill-defined. It's, you know, we are in the realm of quantum field theory, so this is just vastly infinite. So one of the things one has to do is to regularize it. And the specific way one regularizes is to approximate what here kind of appears as geometries, which I haven't specified. It seems I'm looking at smooth objects, but I will now regularize this space by approximating these smooth curved manifolds by piecewise flat simplicial manifolds. Simplicial comes from simplex. So simplex is just a higher dimensional triangular object. So these are triangulations in d dimensions, and of course I'm interested in 4 dimensions. Let me call them T. So I obtain them by gluing together triangular building blocks according to certain rules. The building blocks, by definition, are pieces cut out of a flat space. So that could be a Minkowski signature or Euclidean signature space. There are edge lengths, associated with each building block, and of course the connectivity of the whole thing. So, what am I gluing to what? And these provide a regularized version of the space of all geometries. So I'm looking at the space of, all quantities I can get by gluing together certain flat triangular building blocks. The name dynamical triangulation is kind of a code word for a formalism where basically one uses building blocks that are all identical. So they all have the same size and shape. Yeah? If you go to Lorentzian signature, actually, well, you want to allow more than just one type because you want to distinguish between time and space, like versions usually, but it's just a few building blocks. So, and then your task is to assemble curved piece-less flat geometries from these building blocks. So to make this a little clearer, I've drawn here triangles, which are the elementary building blocks in 2 dimensions. So if I was doing the 2-dimensional path integral, I would build, if I was in Euclidean signature, I would build my curved geometries, piecewise flat geometries, by gluing together these equilateral triangles. So LS stands for space-like edge, and it's in blue here. And by contrast, if I was going to look at Lorentzian space, I would glue them from Minkowski building blocks. So little pieces cut out of a 2D Minkowski space, like so. So this object has now 2 time-like edges and 1 space-like edge. But all the space-like edges are of the same length, and also all the time-like edges are of the same length. And then my task would be to glue these together, subject to certain gluing rules, to get objects that look like, well, like the thing I drew here in the bottom right-hand corner. Yeah, so that's a kind of typical history that you get by just allowing all ways of gluing such building blocks into, in this case, 2-dimensional curved piecewise flat manifolds. Okay, so here there's also hidden in the edge length, there is a UV cutoff hidden. So you see the LT squared, they have just 1 length. I'm using squares to allow me to distinguish between time and space-like edges. So there is a constant alpha here, which I can choose. In 2D, I can just choose it to be anything, positive number. And you see these, the L squared are, of course, positive numbers. So by multiplying by a negative number, I get here a time-like squared length for the time-like length. And what also appears is these are all given in units of some short length parameter, which are called little a, and that plays the role of a UV cutoff. So it's like you're putting things on the lattice, but of course this is only to regularize things. That's not the real thing. In the end, you want to shrink the lattice spacing, this UV cutoff, you want to shrink it to 0, and then only look at interesting things that emerge, that come out when I take such a continuum limit. So what was shown in kind of what got the whole business of doing CDT, lattice gravity, started was a paper by myself and Jan Ambjörn from back in 1998, where we showed that if you use Minkowski building blocks, so that was a new thing at the time, and you express a 2-dimensional whole model of quantum gravity in terms of such building blocks, you get an exactly soluble model, but it's different and inequivalent. So the physics of it is different than from the purely Euclidean thing. And so that was the first very explicit example of a statement I made earlier. When you go non-perturbative, then doing Euclidean gravitational path integral is something really different from doing a Lorentzian gravitational path integral. And so one here sees this very explicitly. And here, just to highlight, I mean, one thing, already looking at the typical histories, that kind of provide, well, the configuration space over which I'm integrating the path integral, they're very, very wild and very, very non-classical. So you should think of them as the analogs of the Nova differentiable path one finds when one does a path integral for a non-relativistic particle, free particle, or in some potential. Yeah, then one finds that typical paths in the continuum limit of the corresponding path integral are also Nova differentiable. Of course, that does not stand at all in the way of being able to derive, say, classical limits from them, you know, in the sense of Ehrenfest using expectation values. Okay, let me zoom in a little bit on that path integral because I want to say a few more things about it. So here again, on the left, you see this formal expression. Yeah, so where we have again the space of geometries over which we are integrating with some measure. And now I've chosen for definiteness kind of an Einstein-Hilbert action where I have a curvature term and a cosmological constant term. Now, so, and kappa squared is of course proportional to the inverse Newton constant. Yeah, G Newton. Now, this is really a totally ill-defined object. So what we do with that, so we make that into a mathematically well-defined regularized object here on the right. And it takes the form of a sum over a certain set of triangulated objects. There is a kind of weight factor here, which is 1 divided by a number, and that number is really the size of the automorphism group of a given triangulation. So if there are non-trivial symmetries, then this is a number that's not equal to 1, but smaller. And each of these spacetimes, this regularized spacetimes, is again weighted with a phase factor, where here now we have what I call the Regge action. That is just this object translated following a prescription of Regge's to what it would be on a piecewise flat space. So that's what this is. And of course, this is the regularized object. And then I have to send A to 0. So my lattice spacing. So we're not interested in finite triangulations. And there is no underlying postulate kind of space-time, is finite, and therefore we shouldn't take A to 0, but should stop at the Planck length. No, that's not the name of the game. But we really aim for a continuum limit where we send A to 0, the UV cutoff, send, of course, the number of building blocks to infinity. That's the idea, while keeping a physical volume, which I call V finite. So in 4 dimensions, that would be the number of all 4-dimensional simplicial building blocks times kind of the unit, A to the 4 unit space-time volume. Okay, so that's the idea. I take a chunk of space-time, and then I have these lattices, the triangular lattices, and then I look at the limit where I keep that box, kind of a fixed size, but I subdivide it into finite bits and check whether there's an interesting scaling limit, as one says. So these regularized space-times are obtained with certain gluing rules, where critical, it turns out, is a rule where you just not glue these kind of randomly together. So here's a 4 building block in 4D, a Minkowski 4 simplex. So, but the rule is you have to glue them in a way such that overall a well-defined causal structure emerges or is maintained. So at the level of the individual path integral histories, you arrange these building blocks in such a way, there's, again, there's of course a little light cone in this building block. Yeah. So basically what you do, you don't allow, the light cones all have to line up in a way. So you don't have, closed time-like curves or funny things, where one light cone hits another one at right angles. So these are, of course, kind of, they violate the well-definedness of the underlying causal structure. So we are imposing really a discrete analog of global hyperbolicity. So that space-time is a sequence of spaces of the same topology. Yeah. And of course, one has played around a lot with these things. You might imagine that you don't have to do that. So you could just say, okay, let me just either, choose some crazy gluings for these building blocks, or start with Euclidean building blocks to begin with, and then hope that kind of an overall direction would emerge, some time arrow. Well, this has never happened. It has never been observed, although people have looked at it. So it appears that this is something one has to kind of put into the path integral as basic information. And if you do that, you get, that makes all the difference in a way between the Euclidean and the Lorentzian path integral. So here I've given you a little sketch of what this means, amounts to in 3 dimensions. Yeah, so this is a 1 dimension lower than what we are interested in. So really you have layers of spatial triangulation where kind of your space-time building blocks kind of interpolate between those slices. And then you have, you stack them on top of each other, and then you get these piecewise flat curved space-times. So what's nice and beautiful and essential, as I said before, is that this way of representing the path integral allows you to evaluate it in 4 dimensions with numerical methods. So to get numbers out, and not, of course, just for the path integral itself, but more importantly for observables that are evaluated in such a path integral. What is essential, since here you are just talking about a sum of complex phase factors, which has a very lousy convergence behavior. What is essential is that, and what we happen to have in CDT is a Wick rotation. A Wick rotation that's well defined, that maps the Lorentzian piecewise flat spacetimes we are starting with individually to exactly one partner Euclidean of Euclidean nature. And this Wick rotation is such as a certain parameter that you are generally analytically continuing in the complex plane. This also converts these phase factors e to the is into both real Boltzmann weights of the form e to the minus Euclidean action. So that's beautiful, and it's a prescription which has, as far as is known, no continuum analog. So it works on these piecewise flat objects, and it's beautiful and essential because it allows us to start from the Minkowskian or Lorentzian object, do the Wick rotation, put it on a lattice, do computations, and then, of course, Wick rotate back the result or interpret back, the result we get there in Lorentzian terms. So that's the name of the game. Emphasizing another huge difference with the continuum approach. So we don't have coordinates. So these triangulations are just described in terms of the edge lengths and the gluing data. You can think of as a matrix of nearest neighbors. And there is no coordinate redundancy. So there are no diffeomorphisms that act on that. I mean, one is really working with pure geometry. So that is a very, also technically, a huge advantage over what one can do in the continuum, where one always runs into big issues of gauge fixing. Do gauges exist? Losing physical meaning once one is in a gauge fixed formalism. So here one is really working in a non-redundant path integral. Okay, here's a little footnote that says, okay, I'm discussing here pure gravity. Coupling matter is really straightforward. I will only make one little remark later on in the talk, but yeah, that's a whole chapter by itself. For the time being, I'm just talking about pure gravity. Okay, so here we're talking about why the gravitational path integral, although, path integral is kind of ubiquitous in physics. That's just a superposition principle, right? So any quantum theory can be formulated this way. Why it's so difficult in gravity. So here again, I have kept my just this line of formula from the previous slide. And now let's look at the major problems this object has on the left. So this formal object. So what do I have to do to really make this into some well-defined prescription? So number one, this, as I already said, this is just a complex object, and we do usually have no idea how to evaluate it. as a sum over oscillating factors. Beyond perturbation theory. So what people often do is they look at a similar problem, but with Euclidean signature. And then the beauty is then, well, you just work with real weights to start with, and you're doing a kind of a path integral over Riemannian signature spaces instead of spacetimes. So I have already told you that this is something different. So you're substituting a problem you can't solve by a problem, well, that's actually not much easier, but at least has real weights. Now, CDT, as I have already said, has a well-defined way to actually get from the Lorentzian to the Euclidean path integral. So it's not an ad hoc thing, but one Wick rotates the space of all Lorentzian objects to a subset of the space of all kind of Euclidean signature objects. And this being a subspace is actually kind of a small subspace, kind of a subset of measure zero. Putting these in the path integral makes all the difference. Now, let's imagine you've stuck, that has been your strategy. Let's just do the path integral the Euclidean way. And that's, of course, a big story that initiated with, in the 1970s with Stephen Hawking and the Cambridge group. Big volumes have been written about Euclidean quantum gravity, that path integral. Now, unfortunately, the Euclidean path integral suffers from another kind of deadly disease, the so-called conformal divergence. That is, if you split up the metric G mu nu into a conformal factor, overall factor times a constant determinant metric, then you understand that this conformal factor, if you just look at it, it's all on the path integral, it comes with a kinetic term that has a wrong sign. Unfortunately, that means that you can make that the Euclidean action is unbounded below. That, of course, is a death nail for any Euclidean path integral. So there you are. Now, what does our way of doing it? We are Wick rotating. Don't we have the same problem? Yes, we do potentially have the same problem, but then one can show that there is a term that comes from the measure in the path integral. So the number of times a specific value of e to the minus action appears, so the entropy of states, that kind of counteracts, if you are in a suitable region of phase space, coupling constant space, that counteracts, that kind of tames this divergence. And the whole thing is well defined. So there's a non-perturbative mechanism that does that. Next, something I have already mentioned in passing, in the continuum, well, you can't do without coordinates, and then you have the trouble of having to get rid of, kind of gauge fixing, typically the diffeomorphism symmetry, which makes your configuration space redundant, by, of course, infinite amount. So here, as I have already said, we have no residual gauge symmetries, and the cutoff, this the edge length is actually a Giudici cutoff. So, it's not affected by any redundancy. So that's beautiful and technically very powerful and important. Now, next point, okay, perturbative gravity is not renormalizable. So anyways, this is highly divergent, apart from the problems I have already mentioned. So how do we renormalize it? So it turns out, just to make things brief, so it's not as badly. It's just it doesn't diverge more than kind of standard quantum field theoretic path integrals, at least in a suitable scaling limit. And one important aspect of this is that the number of configurations at a given volume, discrete volume, seems to scale not super exponentially, but exponentially, and that's important. So it means it's kind of curable divergences. Also, divergences can be taken care of with standard renormalization. Now, yet another reason for why we don't look at this in the continuum beyond perturbation theory. Well, we can only do Gaussian integrals. So, but definitely what we're finding here is not Gaussian. So we need other methods. And here is where the Monte Carlos and the numerical simulations come into place that allow us to evaluate this and get quantitative results. And lastly, a point I want to mention here that does by far not apply even to discrete models of quantum gravity. Why is this a unitary theory? And that's a problem we addressed early on in this framework. And one can show that this lattice regulator theory has appropriate properties under reflection. So it's so-called reflection positive. And that virtually ensures that if you take a continuum, if you can show that an interesting scaling limit exists, that the resulting theory will be unitary. So that's another, of course, big thing. All right, some results. What comes out of this is we're measuring observables and we look at what these observables do. So the observables are quantum observables and they have to be diffeomorphism and invariant for me to be able to evaluate them in the path integral. So here we are in the Euclideanized path integral, the Wick rotated one. This is a quantum observable. So it's just obtained by formally inserting it in the trace, and computing the mean to start with. Now, this is gravity, pure gravity. So a point X and a field at a point X is not a diffeomorphism invariant statement, and the same holds here. So our observables are typically non-local integrals of scalars. And the simplest example would be take the Ricci scalar and integrate it over all space-time. Then you get an observable. So this is the type of things we can study. One could think about what one does usually in classical gravity or in perturbative gravity. One might think of putting in certain, reference frames that take care of the problem or make, choose relative observables. Well, usually this interferes with the strongly quantum fluctuating nature of the physics at that scale. So this is typically what we are reduced to doing. So these kind of integrated scalars. Now, you can, of course, say, okay, but then I cannot, answer all the questions that I want to answer, which are, the entropy of a black hole, resolving the quantum information paradox, because I'm not even giving you coordinates, let alone, allow you to ask very local questions, but only very global ones. Well, that's, again, it's a feature. And you could say, well, then I don't like your framework. Well, but that's part of what this is. The theory is at very high energies. So one has to, that's what I call expectation management. There are certain things that one can extract via observables, and others that are infinitely difficult, or they don't have a Planckian implementation in terms of diffeomorphism invariant theory formulation. So you cannot even formulate them properly. And then, of course, in a way, they don't make sense. So it's more than a technical problem. If you ask me, so what interesting things can we then study? Well, here is a beautiful example of an average observable that's been very important, which is the spectral dimension. So that's just a dimension you associate with a quantum space or a very general space. And it turns out this doesn't have to be, in general, is not equal to the dimension of these building blocks you started with. So it doesn't have to be 4 if you start with the 4D building blocks, because you're taking non-trivial scaling limits. And it turns out that the spectral dimension, when one measures it here in this framework, has a scale dependence. So if one measures it at very short distances, it's not 4, but it's something like 2. While when one then zooms out and looks at it on larger distances, it does become 4, which is compatible with classicality. So that's beautiful. But then there is this kind of quantum signature. So that was found quite early on in this framework. And what is interesting is that over more recent years, this has been reproduced in various approaches, and it's conjectured to be a universal property of quantum gravity. But it's, of course, very, very non-perturbative. You couldn't even dream of it just coming from perturbation theory. So another key result, you could say, is maybe even the key result. I start with these superpositions, quantum superpositions of these crazy spacetimes. Okay, how can this possibly reproduce classicality? But the thing is, well, it can, and we've shown that it does. And by monitoring measuring a specific observable, again, of a quite global type, which is the three-dimensional volume of space at a fixed time as a function of time. So there is a notion of proper time that comes with this formalism. And it turns out, if one measures this, in the sense of expectation values, it matches what we call this volume profile of a classical four-dimensional de Sitter space with great accuracy, although we never put in any background geometry, let alone a de Sitter geometry or made symmetry assumptions. So it's kind of a beautiful result. So one must be careful to interpret this correctly. So I'm showing here a picture. What is one doing here? Well, one looks at, all these, one of these geometries, and one picks out just a single variable, namely the three volume as a function of time. So three volume goes up, time goes to the right, and you see this kind of extended blob structure here. So that's a Monte Carlo snapshot. But of course, what you don't see is all the other degrees of freedom. They're just not in the picture. So don't think this is a nice, smooth-looking de Sitter thing, because it's not. We're just looking at the global scale factor alone. So we're not doing quantum cosmology. So these wiggles, they're still there. So that's also why this result is remarkable. Now, for a long time, we thought, okay, where to go from here? We only can look at global things, and it's not, well, the global volume is a very coarse object. Isn't there something that is more, has the flavor of what one looks at in classical GR, like curvature? And well, after thinking about this for really, really a long time, together with a student of mine, we came up with a notion of Ricci curvature that can be meaningfully evaluated on a crazy, nowhere differentiable space like the one I'm showing here. So that's another long story. I will not go into it, but this is now a notion which we have at our disposal. And it's beautiful because we can look further. Okay, here this is just, let me not go into things, what these are. So these are observables we've measured to, enhance this flavor of this is an experimental science. We do certain measurements, we ask certain questions of our simulations, and it gives us answers. These answers, of course, come with error bars, but they make certain quantitative statements which we wouldn't be able to extract in any other way. So this is, looking at the shape of the universe. These are the eigenmodes kind of this Friedmann factor. So it says something about the quantum fluctuations around the mean, this de Sitter mean. Here is the spectral dimension of the universe, which we are monitoring as a function of diffusion time. And here we see, that it asymptotes to 4, the classical value for large times. But when we come to smaller times, there is this dimensional reduction that takes place. And here is something that maps the average Ricci curvature of our crazy quantum universe to that of a 4-dimensional round sphere, which is the Euclidean version of the de Sitter space, and shows here that there is some match there. So again, just to give you a flavor. So, I'm getting close to the end of my presentation. So talking about the de Sitter space already, smells like physical cosmology. Why? Because the very early universe, we typically described in terms of quantum fluctuations, inflaton, blah, 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 curvature fluctuating on a de Sitter-like background. So what I'm getting out of here just from first principles, from the full quantum gravity theory, might conceivably have something to do with that or might be relatable to it. So kind of what are the statements we can already make about this? Now, we have already found the de Sitter, the match for the overall shape of de Sitter space and the average curvature. That's good. But we can go further. So one thing I want to mention in passing is, well, having a de Sitter space come out does mean, there is a positive cosmological constant floating around here somewhere. And that is indeed correct. So one can show that the renormalized cosmological constant in this whole setup has to be positive. So in a way, we are ruling out anti-de Sitter space, which is not bad because, this is not what our universe seems to look like. by the way, this is not a fixed constant, but only what is only fixed as a prediction is that it has to be positive. It can be arbitrarily small. Yeah. Now, so what we've derived also to, again, bring back, what is this about? We're running these simulations on, lattices of maybe up to 1 million building blocks. And what they explore, that's what we understand from looking at the dynamics, is really a region of very close to the Planck length. So of up to universes whose size is up to about 20 Planck lengths across. And what I've shown you are some observables where we've been able either to find a genuine quantum signature or some resemblance with classical geometry as known from GR in the sense of expectation value. So not only, for instance, can we look at the shape of the universe, but what we've also been able to do simply by analyzing something that's called the volume-volume correlator, the three-volume correlator of this universe, we've been able to reverse engineer the effective action that gives rise to that as a solution. Yeah, in the sense of being kind of the lowest energy state in the Wick rotated path integral. So let's go back to matter. What about matter? Well, matter, of course, opens a whole new dimension. It's easily integrated into this framework by simply making a double path integral over all geometries. And on each geometry, we're putting a full-fledged matter model of whatever it is. Here, phi stands generically for matter fields. And then, well, I should have maybe already Wick rotated, but it doesn't matter for the point I'm making. And then we're just simulating the combined matter gravity system and see what we get. Now, preliminarily, what we can say, of course, we have run experiments like that, looking at the combined system near the Planck scale in this scenario. We haven't found that the matter fields have a very significant impact on the geometry. So a possible conclusion is that matter doesn't matter at that scale very much. What's dominating the whole story is really the geometry, is really the gravity. So now, independent, so this deserves further study, but independent of this, there's now a clear roadmap to connect to phenomenology, and our best bet is kind of early universe physics. So here's my next to last slide. So where do we go from here? We are confined to these very global observables. So how can we ever connect to anything, that has a flavor of local geometry? Well, we have to look at more fine-grained observables, and this new notion of curvature helps immensely. So I give you two examples of observables we are looking at. The first one is an observable that will enable us to make a quantitative statement about how homogeneous and isotropic our crazy quantum universe is. So it has the shape of a de Sitter thing, but underneath are all these quantum fluctuations. So you have to come up with a way to quantify. You want to be able to say that at a certain coarse-grained scale, well, thinking of that as a homogeneous space is a good approximation. But you need a diffeomorphism, nonperturbative homogeneity measure in order to be able to do that. And we've developed a prototype in 2D. So at least as interesting are in kind of resolving more local structure are two-point functions. So here, yeah, the two-point functions exist. Diffeomorphism invariant two-point functions exist. And again, we've made a pilot study in 2D that beautifully measures a curvature correlator. So since everything has to be global and diffeomorphism invariant, these two-point functions come with a twist. So here I've written down how to compute it. So here we have the sum over geometries normalized. So what we have to look at is, well, give me a local scalar, like a Ricci curvature, insert it at a point X, insert it at a point Y. But of course, yeah, I'm not allowed to point to individual points. That doesn't make sense, right? So what I have to do, I have to integrate over all point insertions X and over point insertions Y. But in order that not all information is washed out, I force them to be, to have exactly a geodesic distance, which is geometric, R. That's what this delta function does. So then I can study this object as a function of R. And then I can see how it falls off, or is it zero, is it non-zero? So we've done it in this 2D toy example. This works beautifully. And well, there's some, lattice artifacts here. And we are looking at 2 points, and these are kind of, the curvature is extracted from a little, why is this a little bubble, a little circle? Well, it's slightly, it's only quasi-local because it involves, derivatives. It's a curvature. So it's in point X and point Y. And we see that when you look at sufficiently large R's, where these regions, these measurement regions don't overlap, it's beautifully zero.
Sorry, are you on a given space slice for that?
No, this is in space-time, in 2D. Okay. So it's Wick rotated. So we integrating over all pairs of points at distance R, regardless of whether they're time-like or space-like separated. So that's what comes out. But what we see is there are no correlations. So in 2D, this is exactly what you would expect, because there are no propagating degrees of freedom. But of course, this should just be a warm-up to higher dimensions, where we want to do the same thing. So, but this just shows, as a proof of principle, that this works. And it's not an easy computation and easy setup, but it's something that hopefully will relate nicely to exactly the kind of things that people look at in early universe cosmology. Correlation functions are, one very essential thing to study the universe at, slices of constant time, for example. Well, there are many things to say, but let me wrap up, and then, we can have further discussion and questions. So what I said is key to quantum gravity, in the way I think about it, is to have non-perturbative path integral, to tell it to be Lorentzian, and require it to have good causal structure before you take even the superposition, work with dynamical geometry. So random geometry is kind of the key technical mathematical term that underlies this, and have a numerical toolbox. So the ingredients are fairly simple, but to show that the path integral, is well defined and computable, has taken us, 20 years. So that is very non-trivial. But now we have this, it's working. And now we can just focus on the physical questions. Yeah? So it gives us a window on this truly non-perturbative world near the Planck scale. And there are many surprises. Most things don't look classical at all. But we ask physical questions, and we have to find the right observables here to tell us, to answer what are good questions. So as I said right at the beginning of my talk, well, we've thrown out the G minus and the tensor calculus and the coordinates, but this is very much in an Einsteinian spirit. So you're thrown back at having to formulate physics without coordinates, which of course can be very misleading. So you have to really think in terms of geometry, and that's one of the beauties and strengths of this approach. So how do you get back to the standard picture? Well, everything has to be generated, recreated dynamically from these quantum fluctuations. But of course, we have already seen successes. So, whatever the average geometry is that emerges on large scale, a notion of scale that is being generated inherent in certain observables that we measure. So it's all, it's a consistent picture, but it's very beautiful. It's very geometric. It's quantum geometric. So it throws also new light on what we mean by solving quantum gravity. So if you look at typical talks that people give about quantum gravity, it will start with motivation, the things one wants to do. And let me quote again, solve the black hole information loss problem, resolve singularities, many questions that are very, very closely, that come from problems we find already in classical GR, and they're typically formulated in, well, not in a background-free language that would enable us, to even in principle address them in this very non-perturbative diffeomorphism invariant framework. So what quantum gravity really is, maybe much more like, a very strongly coupled, strongly quantum fluctuating theory near the Planck scale, which you can only access or maybe primarily access with the type of tools that I've introduced to you here, which are more things you would use maybe in condensed matter systems. Yeah. So where we also don't have a strong analytical foothold on what's happening, but we're looking at other things. We're looking at universal properties. We're looking at universal scaling exponents. We're looking at effective descriptions that, give us an idea of part of what the system does. As I've already mentioned, for the Friedmann scale factor, we can actually extract from numerical simulations like a cosmological action. So this is the way, it seems to be going if one takes this route. So if you're intrigued, if you also want to become, an experimental quantum gravitator, for instance, you may look at our new users guide. There are also things online about the simulations. And here in these reviews, there are many, many more details, but I think that's a good moment to stop. And thank you very much.
Great. Thanks very much, Renate, for the really great talk. If there are questions, I'll ask people to, for now, raise their hands virtually, and I'll go through what I see in order, and then maybe things will open up. So, okay. So the first question that I see we have is from, I hope I pronounced it correct, Jan.
Hi, Renate. Thank you for your talk. Please, I have one question concerning cosmological constant in causal dynamic triangulations. I saw here that, one of the tests of quantum gravities is the application in cosmology, and I saw some article where there was origin of cosmological constant in causal dynamic triangulations. What I saw from your talk that I need to plug in the cosmological constant into the theory. Is it correct, or?
Well, there are two things. So there is, of course, when you work with a regularized lattice model, you're using the Einstein-Hilbert action, and there is a bare cosmological constant. But that bare constant is, of course, not the physical constant. So it only becomes physical after renormalization. So here in all, whether CDT or DT in all these models, this bare cosmological constant is additively renormalized in a way we understand really well. And then the statement is that the renormalized constant that comes out of this, well, it's still a free parameter of the renormalized theory, but it cannot be negative. That's by the way we take the scaling limit and continuity is taken. It's forced to be an undetermined but positive constant. So we are not determining it. So we don't have a prediction, that comes out of this framework, but it's just, one bare constant is exchanged to a renormalized constant, but it's still a full parameter.
Thank you. And my second point is what is very interesting is that actually causal dynamic triangulations is fixing the dimension to the dimension 4, and it's with a strict disagreement with string theory, for example, where we have the higher dimensional spacetimes. It's possible to do the triangulation of also in higher dimensions, or it's very general question.
Yeah. Well, people have thought about it. Of course, 30 years ago, further ago, 40 years ago, no one would have even asked that question. Can you also does this work in 26 dimensions? Well, the thing is, of course, again, one has to distinguish, what I'm putting in are these building blocks. So you could say, well, they are motivated in a way by the degrees of freedom of the classical theory. Yeah. So, and of course, I can triangulate, 4-dimensional manifolds, and then I have exactly these building blocks. But nevertheless, once then I put them into the path integral, that's the first statement. What comes out typically is, of course, complete gibberish. Has nothing to do with 4-dimensional continuum anything. Yeah. So like the Euclidean, models. So one statement is here: if you start with the 4D building blocks, and they're of course associated with a certain, action, right? A discretized version, if you like, of the Einstein-Hilbert action in 4 dimensions. Of course, this action is different in all dimensions classically, and of course it has a certain number of dynamical degrees of freedom in the continuum if you start there. So then you get what I've briefly talked about here. We already know what happens when you start in 2 and 3 dimensions. Then you definitely do not get an interesting 4-dimensional kind of quantum gravity theory out. People in the old EDT models, they've looked at things in 5 dimensions and 10 dimensions. The problem there is that even if you do, well, you get these degeneracies of the path integral. So this Euclidean path integral is kind of sick, if you like, without these causality conditions. And well, what you find is that these sicknesses persist in 3, 4, 5, and 10 dimensions. So yeah, you get nonsense. We haven't done the whole thing in CDT because we are happy if this gives something interesting. And there is no deep reason, to believe that starting with 5-dimensional building blocks gives you something interesting. I cannot exclude it, but I think it's not a good criterion for a physical theory, and it never was pre-string theory, that a theory has to kind of work in all dimensions in order to be, kind of physical and good. So I think I would just throw this criterion out of the window. We could have found, when I said we looked at the spectral dimension, of course we could have found that at short distances that the dimension wants to be larger. What we found is that it goes to 2, but in principle it could have gone to 10 or 11, and then we would have said, hello, we understand that this is a theory that dynamically really wants to be higher dimensional at very short distances. But this didn't happen.
Thank you.
Next, we have a question from Lee Smolin.
Yes, can you hear me?
I can hear you.
Yes, Renate, I think remarkably, we're coming pretty close to each other. The one thing I would add to your formulation is that one way to make these quantum diffeomorphism and invariant functionals is to invent a game such that if you win the game or lose the game, it defines a diffeomorphism invariant functional of the geometry. And I can show you a lot about that another time, but I think it's a new kind of invariant that could be very useful in your context.
But will that give me new invariants on top of the ones
No.
I know about? No.
Yes.
Okay.
Yes. Because, for example, the fact that you get positive de Sitter and rather anti-de Sitter corresponds to the possibility of winning. Because if you can collapse the universe, you can win.
Okay. But there could be other possibilities. That's what you're saying.
Oh, sure. Many games.
Okay. Yes.
Okay, thank you.
Okay, so if anyone has any other questions, please raise your hand. I'll keep an eye out. In the meantime, I had a question. You mentioned at some point about how unitarity comes out here, and it's something to do with positivity under proper time inversion.
That's right, yeah.
Yeah, could you explain a bit more about what that is and exactly how it becomes unitarity?
Yeah, so in a way, so that's how in, let's say, standard lattice QCD, right? I mean, of course, lattice gauge series, you want them to be unitary, at least in the continuum limit. So what you always check is that you set up as a discrete model such that it has this reflection positivity. So that's not part of what you find in standard QFT textbooks, but it basically comes from the existence. Of course, even if I do a path integral normally, what's behind there is, of course, I can think of it as a canonical. I mean, there's of course a canonical formulation, right, where I think of states at fixed time, and and the Hilbert space, which will, for instance, appear explicitly when I choose boundary conditions, say, from a path. But anyway, so one always thinks there's something like that in the background. So because the unitarity is typically formulated, of course, with respect to a given time, and the way it appears is, that's a time is conjugate to a Hamiltonian. Yeah. So, and unitarity, of course, is e to the ith, right, where h is a self-adjoint operator. So the question is, how do you formulate such a condition on the lattice? And it turns out the right thing is this reflection positivity, in a way, under time reflection. And the thing is, this is kind of a Euclidean analog. Yeah, if you think of standard QFT, is of course with Minkowski's signature, but then we have the Osterwalder-Schrader axioms that tell us when we can think of that really in Euclidean signature, and by what way do we analytically continue the endpoint function of the theory. So all of this formalism also works on the lattice. And it turns out that kind of unitary conjugation in the Lorentzian theory is time reflection in the Euclideanized theory. And if you show that your theory, your lattice theory, has these reflection positivity properties, that is just a Euclidean way of saying it is unitary, or the associated kind of transfer matrix has the right properties on the lattice. And well, so for this, in order to be able to say this and to talk about unitary, of course, you need a time. And here, we have a kind of notion of proper time, which is part of our lattice constructions. It has this, kind of stacked structure. So it is meaningful to formulate this condition of reflection positivity. And it turns out that in 2, 3, and 4 dimensions, one of the earliest papers we wrote about this around 2000, we showed that the regularized theory has this property. And this, is maybe not strictly necessary to obtain a unitary quantum theory in a continuum limit, but it virtually reassures you that this happens if such a limit can be shown to exist. So that's what unitarity is. So it's very gratifying that this seems to be here. Yeah. Of course, it doesn't mean that it solves all. Well, does it solve the information loss problem? Well, it's a different question. It's a very specific question, but it solves it in the same sense as certain string theoretic arguments say, well, our theory is unitary, so this problem cannot arise. So whatever I'm doing, whatever situation I'm describing, things must be arrangeable in such a sense that they're unitary. But I think that arguments fall short, but at least what we are doing is kind of bulk unitarity, so the theory, our theory seems to have it, which is nice. And typical discrete models of quantum gravity or lattice formulations, they don't have that. And that was something that was discovered in the 1970s and early 1980s, when people for the first time put gravity on the lattice, but kind of in different formulations, not in this geometric formulation, but more like using gauge theoretic formulations of gravity. And then it was actually Pietro Menotti from Pisa who showed that many of these models are not reflection positive, so they lead to non-unitary theories, if they lead to anything. So yeah, so it's a non-trivial statement that this here satisfies it. Does this answer the question?
Yeah, absolutely. Thanks. So we have another question from Taehyun Lee.
Thank you very much for nice talk. I have a very elementary question about, because I'm concerned about lattice theory, even if we take actually limit a equals 0, still actually you can trace this absolute background, because when you start with the lattice theory, I mean not only lattice gravity, maybe any lattice theory, we start with the lattice, and then you take actually continuum limit. But in theoretically, we can always trace back to this background. This background, you cannot actually simply remove this intrinsically. You remove this background, make every actually theory is completely covariant to the any observers. So that's my concern. How can we? Because what's the actually region? Actually, we have to start with the lattice theory. If that's not the case, I mean, we can start with just continuum theory from the beginning, but there must be some reason we have to use a starting point with the lattice structure.
Yeah, so if you're talking, I'm not, let me try and whether I can understand, you know, or rephrase what you said. So I mean, I would agree with you if you're talking about standard lattice field theory. Yeah. Then I put this on the lattice, and that lattice is really a representation, say, of, you know, 4-dimensional Euclidean space. Okay. So its metric properties are, although we don't state them explicitly, well, they are put in, you could say, by hand. Yeah. And they obviously, well, they will survive the continuum limit. So this is what I would call a background, although it's not usually stated this way. But what we're doing in gravity is something different. We do not have a background. So we are not choosing one lattice, but you know, we do these triangulations. We are not fixing one triangulation, but we are summing in the path integral over all possible triangulations that can be obtained from these building blocks. So it's kind of a very democratic thing, and no single triangulation is distinguished or serves as a background.
I see. And but in middle of your talk, actually, you said there is no actually gauge freedom.
Yeah.
So
yeah. Well, that is not there for a different reason. That is there because I never introduced coordinates. You see? So I only work with these building blocks, and the only thing I give you are the building blocks, and I'm giving you, you know, the edge lengths of the building blocks. And in the interior, I say they are flat, just by assumption. So there are no coordinates anywhere. So therefore, there is no redundancy. Well, you see, well, in a way you can say, of course, when we start now doing physics with these triangulations, and we put it in the computer, of course, I have to give a label to these building blocks, because otherwise I'm not sure where I am, right, in these triangulations. So, and that's what we do. So we label them. Then you can say, but this is the analog of coordinates. In a way, that's true, but it's very easy to get rid of this overcounting of the labeling. And this is kind of even inherent in the way you set up the Monte Carlo simulation. So it's taken into account in a very, very easy way. And that's, of course, not true for diffeomorphisms in the continuum. Now, so.
But it actually corresponds to the diffeomorphism, because you have all different actual triangulations. So you can map this all different triangulation with the diffeomorphism in continuous limit or
no. Really labeling this relabeling symmetry is not in any way related to, you know, a diffeomorphism, which of course acts and transforms the manifold into itself. No, there's no way, unless you go close to flat space and, you know, do kind of flat space approximation. But it's a different thing. You can say, morally speaking, it's the same because I give certain names, to certain objects in my theory, but the technicalities have nothing to do with each other.
Okay, thank you very much. Thank you so much.
Great. So our next question is from Richard East.
Hi.
Hi, lovely talk. So I confess I missed the first 10 minutes for other reasons, so perhaps there was something in this that revealed the answers to everything I'm about to say, in which case I'm a fool, and sorry for that. Yeah, basically, I was interested in this triangulation approach, mostly because I do a lot on like quantum computing, quantum information stuff. In particular, I have this interest in something called permutational quantum computing that you may or may not be aware of. But it looks like you have triangulations. This is like your initial states. And then you have certain computations on top, which look like adding tetrahedra. And in the past, I've looked at this through like the LQG line. I mean, okay, your triangulations, they're here, but dual to the spin network. There's a way to encode spin networks, nice enough. And I use like the ZX calculus to model these things. Right. And I was just wondering, looking at this work, to your mind, is there scope to try these techniques for things you're looking at? I mean, there's some distinction here, which I think is a bit too subtle for me. Again, maybe you mentioned this before, between these tetrahedra that you see here and the tetrahedra that exists in the LQG model. But I mean, I guess a trivial thing in my mind would be, okay, well, I just say, okay, you've got these tetrahedra. I would model them through spin networks and just say, okay, that's how I constructed these tetrahedra if you're interested, all these triangles you're interested in, sorry. But maybe there are more approaches to this. Sorry for the vagary that's floating around in my question. I'm wondering if you have any thoughts on this.
Yeah, okay. I mean, simplices are, of course, very nice kind of elementary building blocks. So many people have played around with them in many contexts. So one thing I want to say here, so really what you see here is, of course, space-time building blocks. And the gluing rules are such that what you're putting together from these, 4 simplices are simplicial manifolds. So that's a fairly strict way of doing the gluing, because if you do arbitrary gluing, this is 4D building blocks, you get things that are called pseudo manifolds and much worse. Yeah. So the problem with those is that there are very, very, very many of them, and they, as a function of the volume, they typically they scale super exponentially. So the number of all ways of putting them together is kind of uncontrollably large, super exponentially large. So one has to see, in a certain formalism, what is the class of objects one is actually looking at. So what's the difference between, with the spin foams? Number one, the spin foams, well, they don't have any manifold conditions on them, and they have additional labels on them, and spin labels. So I have nothing of this at all, and whatever statements I'm making about the dynamics that I'm seeing in my model here, I don't think has any immediate ramifications or analog of what spin models do.
I guess I brought up these spin models as, I think, maybe unfortunately, because this is just the way that I've tried to tack these two things together. Yeah. Okay. I guess what I may be saying is there's this permutational quantum computing model, which it looks like you have triangulations and you have simplices and you have mappings. And perhaps some restrictions that you're suggesting would have computational implications in this computing model. Yeah. I mean, perhaps that's just a point that might be of interest.
Okay, I think one point one has to be also careful about, where I started, I was saying this is not a space-time construction, that many, kind of quantum information flavored things are really spatial constructions. And then you can do things like, okay, I start with, what happens on a kind of time slice, and then you can start gluing simplices onto that and kind of have an idea of like many finger time, this kind of thing. So people have played around with this, not in this DT and CDT context, but in the Raja context. So in the very old days, I mean, Foutini Markopoulou was thinking of something like this. Maybe Lee was also involved in this. More recently, in a Reggie context of Reggie triangulations, which have, of course, variable edge length still, Bianca Dietrich and collaborators have looked at evolution models for kind of Reggie geometries. What we do here are these, there are different things. They are equilateral objects. So in a sense, they're much simpler, but they're also not very much geared toward classicality as such, right? Because they're kind of coarse-grained objects, and you're not allowed to vary the edge lengths. So whenever you want to bring in our continuous parameters, they don't match very well, my context, because we are going for all possible gluings. This is what this random geometry is. All possible gluings of basically identical building blocks, and that's the strength. And they're all of the same size. If I were to bring in extra variables like the length of these edges, then I would kind of duplicate degrees of freedom in a path integral. So it's a different ball game in a way.
Okay, thank you for the answer. I'm not sure. I think you could do things with just fixed triangulations in this particular computing model, but it would be certain.
Depends on what. Depends on what. Again, also, you want to keep track just of the topology of the thing, or really the metric properties, and So
I think some of the questions you're asking, people don't even say in this world. They're thinking very computationally. I mean, they would, I guess, like to connect to this world, but it's not quite glued together. But it's very interesting to hear your thoughts on this, and very useful. So thank you.
But would need to look at really at the details. What are the degrees of freedom? What does this model try and do?
Of course. Thank you.
Okay, our next question is from, I hope I pronounced correctly, Mauricio.
Hello, can you hear me? Yes.
Yes.
Hi. Well, thank you very much for the talk. It was very insightful and instructive. I wanted to ask you about, in the context of cosmology, in early cosmology, and the physics you can do with causal dynamical triangulations. We have this paradigm inflation that many people may criticize, but it gives something that we can compare with observations of power spectrum, CMB, and obviously one can put a scalar field and you can try to do something there, but that is in the context of semi-classical gravity. However, there are all these other models along the lines of Stravinsky model that are purely gravitational, or you can interpret it as a gravity plus quantum fluctuations, and can trigger something similar, can trigger inflation, and a very good candidates for that. Can you use CDTs to make this bridge to connect the non-perturbative regime to the semi-classical regime of what has been already observed? Has been done something along these lines?
No, that's an excellent question, and that's exactly the roadmap, is to strive to build this bridge. So it is very, very non-trivial. So in principle, so the dream is the following, right? So we have this kind of ab initio, first principles, quantum, quantum foam, and now we have this emerging de Sitter-like object. And what I was working towards was to say, well, in order to compare it to early universe, anyway, I have to start studying objects that are much closer to the types of things one studies in the early universe cosmology. The framework is totally different because, the setting there is just, okay, QFT on curved background, in kind of mathematical terms. Whereas I'm struggling. I mean, I don't even have I don't have a background, so I'm looking at certain observables. So looking for things that measure, approximate or quantify approximate homogeneity, that's one step. But say, let me zoom in on the 2-point function. So that's an extremely interesting object, exactly because a lot of what people do, they study the power spectrum, etc., is just 2-point or n-point functions. So as you probably know, from what you say. now, can we directly compare this? Well, it's very difficult. I mean, a 2-point function in non-perturbative quantum gravity is a different animal from a 2-point, perturbatively obviously calculated in very low order perturbation theory, gauge fix, from what one can do coming from the continuum side. So it's really a question. So I've scanned all the literature of how far has this been pushed, like on the zeta-like backgrounds, in terms of, let's say 2-point correlators. Well, these is a very far cry from the things I can study, hopefully in 4D, with my non-perturbative correlators. So number one, I'm interested in what should I expect? Imagine now I can do this curvature correlation functions in the full 4D theory. So is there a prediction, from the continuum theory that would say anything about this? As far as I can see, no. Again, beyond what people study are correlators of G mu nu, G kappa lambda, which is of course gauge fixed. So it's very difficult to start with to compare, and I cannot talk about G mu nu at all. So I have to go for a curvature correlator. And this is already an object that is very, very complicated, even perturbatively, to study. So I would say, yes, I have hope exactly to create such meeting points. But in the first instance, I don't think there's nothing concrete I can compare to. But what I still can do is to say, okay, look, I'm in the best of all worlds. I study this thing. Let's say, first I studied I study space-time correlators, and let me look. Maybe they have a certain fall-off behavior, and is that an indication that there are kind of gravitonic excitations present, even in this crazy Planckian regime, or something? Okay, that would be one thing to look out for. Then we are looking at correlators on fixed time slices, which would be kind of the natural thing to compare with the cosmology. So again, can we make a prediction? Of course, well, our fluctuations will be non-Gaussian, very likely. But is there a way, or are there clever observables I can think of, to compare to what one might see in cosmology? So maybe it doesn't go via the comparison with the analytical perturbative calculations, because they are very far away, and I don't see any way how technically they could come anywhere near these computations. But again, in cosmology, people do start talking about, how do we describe situations where there are large fluctuations? And how do we handle this computationally? So I looked at some of these things. Well, maybe there is kind of convergence from both sides. Also, people, for instance, are very interested in, what would be the effect of primordial black holes? Then you also get very quickly to a situation, that cannot be described perturbatively. So, so I have great hope, but this is really that bridge, with two very, different, coming from two very different ends to, find something that connects them. Good observables are really a crucial ingredient there. So any good ideas are welcome, but that's that's where we want to go, definitely.
It's a challenging question. Thank you for the answer.
Okay, we have a question from Ding.
Hello. I have a question about the measure term in the path integral.
Mm-hmm.
Do you think it might be necessary to take a non-trivial measure term to obtain the correct continuum limit for higher dimensional path integrals of CDT?
I would say until now, there's absolutely no reason to deviate from the simplest, well, it's kind of geometrically motivated measure. This is kind of the democratic measure in this particular class of triangulations I'm looking at. And well, we see all these nice results. And of course, what one also should be aware of, that there is a large degree of universality, in these models. So, tinkering around with many of these discrete ingredients will not change anything. So, for instance, changing around the way you discretize the action, or maybe even adding explicitly, different terms in the action, modifying the measure in certain ways. These are things that have been studied very much in the Euclidean, the EDT case. And why? Because people didn't like the result, of what came out of EDT, and they kind of stood on their head by changing, the action, changing the measure, and everything always led to, this branched polymer phase. Well, there's still an iteration going on where, exactly people have put, so this is a work by the group of Jack Lyho and collaborators at Syracuse. So they're still trying to make sense of kind of the Euclidean version of 4D quantum gravity with the Euclidean dynamical triangulations in 4D. And they're putting exactly another term in, a measure, term, just something like, or roughly speaking, it's kind of some coordination number to some power term, and then that power is an additional free parameter. And then they have some hopes that if they go, to the end of some transition line where there was very, very, very large values of this power, that something interesting might happen. But in general, a lot of these changes for the discretized theory, they're covered by universality. And for the case of CDT, we haven't had any, well, there will also be such a large degree of universality. So some changes, will simply not matter to what we are seeing. And we know a few things we have played around with that confirm this. But also we don't see any reason to change things as long as we see physically interesting results.
I'm thinking of your work on Lorentzian CDT in 2D. There you can solve the path integral analytically, and then you take the continuum limit.
That's right.
And from learning your work, I see that you need to introduce the so-called renormalization of cosmological constant term.
Exactly.
To take the limit.
Yes.
And then in your first paper, I think what you did is you did a Wick rotation to the Euclidean signature and then take the limit. I was wondering, if you don't do the Wick rotation, then this renormalization term, for example, for the cosmological constant, can I view that as actually a measure term, so that because it stays as a magnitude in front of the phase for the amplitude.
Yeah. So I mean, one thing, I don't know, in some very early iteration of what we did in 2D, we tried to make sense of analytically continuing lambda. But this doesn't really work because it doesn't survive renormalization in a way. So what we did then, I mean, later is we really analytically continued in T, both before and after taking the continuum limit, and that kind of does work. So that's maybe just a side comment. Well, in general, is of course difficult if you want to stick with the Lorentzian framework and then with the factors of I, to show certain convergence properties of the path integral and the continuum limit. So it's really in that sense a very a technical reason for why one makes a Wick rotation. And in 2D, it's possible very explicitly. And I think one shouldn't think of the Wick rotation as something kind of magical and maybe also not necessarily unique. It just, you're looking at, like what you do in QFT, you're looking at certain quantities to be endpoint functions, and you just analytically continue them because that makes the computation easier. But of course, you need to keep control of where your singularities are in the complex plane. But once you do that, it's a completely think of it as a computational trick, right? Just to evaluate the path integral and then continue back. Of course, we cannot do any of this very explicitly outside two-dimensional toy models or cosmological models where effectively it's just quantum mechanics of a few degrees of freedom. Then you can do very explicit studies, you know, of what happens in the complex plane. So it's much more difficult to do any of these things explicitly in higher dimensions.
Difficult in higher dimensions. However, in 2D, we can do this thing explicitly. And then I think it's possible that we don't do the Wick rotation, but still take the continuum limit once we do the renormalization, because in 2D things are simple. In this case,
I don't know. I also, you see, well, that might be possible. I mean, you should show it explicitly, but also we know that kind of their universality classes of pure gravity models in 2D are very sparse. So we know of two universality classes. One is basically the Lorentzian one, and the other one is the Euclidean one. So whatever,
don't count.
Are you suggesting to get something different in 2D, or one of those two?
This is a follow-up question. In 2D Lorentzian signature, you don't count Ojava-Lifshitz as a distinct.
No,
so think of
no, in
dynamical triangulation and locally causal dynamical triangulations.
No. I mean, as I say, no. It's not distinct. I mean, there are two universality classes. One is the universality class of CDT, Ojava-Lifshitz, kind of continuum path integral in proper time gauge by Nakayama. That is one universality class. And the universality class means a certain value of certain critical exponents, spectral dimension, Hausdorff dimension, and kind of gamma string. And then there's the other universality class, which is DT, Liouville gravity, certain tree models, and they just come with a different set of critical exponents. And so far, there's no other classes that are known. So if you say, okay, I have another way of solving 2D gravity.
Wait, that's what I don't get. You also studied locally causal dynamic triangulations in 2D.
Yeah.
Calculated, I remember, if I remember correctly, Hausdorff dimensions, which seem to differ from CDT. Is that right?
Well, these results were inconclusive, unfortunately.
Then I guess you should say we don't really know if there's an additional class.
But from analytically, we know of two classes, and that's also, when we came up with this modified model, our first question was, is it in this class or this other class? But unfortunately, there may be other possibilities. That's why I'm putting you. It would be extremely interesting. People have looked for those. I mean, not just us, but other people have looked for those. Are there other universality classes in 2D in these toy models for pure gravity?
And you still don't see the possibility that a non-trivial measure term plays a role in the continuum limit.
What measure? What measure?
Do you see the possibility that if I want to take the correct continuum limit for CDT, I might need a non-trivial measure term in the sense that it's a magnitude in front of the phase for the path integral amplitude?
Well, I think again in 2D, nothing very much happens if you put a measure term. I think that
if I take away the renormalization of the cosmological constant term, I probably won't get the correct continuum limit.
I have no idea, what kind of changes of the rules of the game you're talking about, but certainly people have, looked at, this is old work by Christians and Di Francesco et al. Of course, they have put higher order kind of an R squared term in 2D in CDT. You can think of that again, it's a part of the.
Maybe I can specify.
But you can think of it as a measure term, and it doesn't change the universality class of the model.
Yeah, maybe I can specify more clearly what the rule of my game is. So for each path integral configuration, I assign an amplitude. That's a complex number, right? in general, it can have a non-trivial magnitude. It could, maybe it's not 1. Usually it's e to the is, that has magnitude 1. But in case I assign a different magnitude, I count that part as a non-trivial measure term.
Yeah.
Because it doesn't belong to the phase.
Yes.
If I add higher order terms in the action, I don't count that as a measure term because it doesn't change the magnitude. However,
well,
the
depends, of course.
magnitude
If you Wick rotate it, of course, yeah, these two things are very much the same.
But if I want to stay in the Lorentzian signature without,
sure, you can do that. Yeah.
Then I can distinguish unambiguously between a measure term and additional terms in the action.
To some extent, yes.
Yes, and then now I want to take the continuum limit. I'm asking, maybe it's necessary that I have a non-trivial magnitude to obtain the correct continuum limit.
I don't know what the correct continuum limit is in your way of thinking about things.
Well, in 2D...
Sorry, so I think at this point, maybe this is a conversation that we can move.
We're going a little bit on a tangent that may not be so interesting for other people.
So we'll move it to the... so in fact, I think we have no other hands left, actually. So what we can do is I think we can end the... we'll end the formal talk here, and then if people have time afterwards, then of course they can discuss further, but if they have to go, also great. So I think this is a good time to say thank you very much to Renate for a really, really interesting talk and for sticking around for some really long and interesting discussions. It's really appreciated. So on behalf of everyone, I'd like to thank you. And at this point, I'll end the live stream and the recording and formally end the talk.